Welcome back, grade 10s. In today's lesson, we are going to continue with electric circuits, and in this lesson, we are going to learn about voltage. Now, in the last lesson, we ended off by discussing current, and we learned that current is the rate of the flow of charge. And what that means is how fast are the electrons running through the circuit. However, those electrons would not have the energy to run through the circuit if it wasn't for voltage. Voltage is the energy given to those electrons that pushes them to move through the circuit. So while current is the electrons that are running, voltage is that push that allows the electrons to run to begin with. We're going to define voltage, and we're also going to understand that potential difference, EMF or electromotive force, and terminal potential difference mean something that is very similar to voltage and are all measured in volts. However, we will describe the differences between them and define each one of them. So let's start. In a closed circuit, charge has the potential to flow. So that means that electrons have the potential to run around the circuit. However, those electrons are not going to move unless there is some type of force or some type of energy or push that drives those electrons around the circuit. So something needs to give those electrons a push to make them run around the circuit to begin with. And that force comes from the cell or the battery in the circuit. What is the difference between a cell and a battery? Well, as already mentioned, a cell is a single electrochemical unit, and a single electrochemical unit has a positive terminal and a negative terminal, while a battery is made up of two or more cells that are connected together and they work together. So if you have a battery made up of two cells, then each cell will have its own positive and negative terminal. Now, a cell has the potential to drive charge or push electrons around a closed circuit. Inside the cell, there are chemicals, and those chemicals are carrying chemical potential energy. In a closed circuit, chemical reactions start to take place inside the cell. And those chemical reactions then convert that chemical energy into electrical energy by pushing electrons out of the cell, and making those electrons move is what creates electricity. Now, voltage potential difference, EMF, and terminal potential difference are very similar terms, and we are going to describe each one and define each one, starting with voltage. What is voltage? Voltage is the work done per unit charge, and that makes sense because remember that voltage is that force available, that push available, which is work or energy. Work and energy mean the same thing in science. It is the work done to push the charge through the circuit, the charge being the electrons. So remember that voltage is that push to get the electrons to move through the circuit. It's that energy needed to move the electrons around, to give them that energy to run around the circuit. So voltage is the work done on, or the energy spent on, the charge or the electrons to make the charge or to make those electrons move through the circuit. And voltage may be calculated as per the definition, work done per unit charge. That's the same thing as energy spent per unit charge. So V is E over Q, or V is W over Q. It doesn't matter if you use E for energy or W for work. Energy is always measured in joules, as is work measured in joules. So this energy is the energy used by the electrons to give them that push to travel through the circuit, and that's measured in joules. Charge is based on the electrons that are moving through the circuit. Remember, each electron carries a little charge, and based on the total number of electrons running through the circuit, we would get a total charge measured in coulombs. And finally, voltage is that work done for every unit of charge, and that is measured in volts. Recall that a volt is measured as the energy for every unit of charge. So it is actually a joule per coulomb. However, we don't call it a joule per coulomb, even though that is not wrong. We call it a volt. As we already mentioned, voltage, potential difference, EMF, and terminal potential difference are terms that are used almost interchangeably. They're all measured in volts, but there are some subtle differences between them, and we are just going to identify what each one of those is. Now, voltage we just defined as the work done per unit charge. When we talk about the potential difference, we are really talking about the voltage drop between any 2 points in a circuit. So what do we mean by that? Let's consider this circuit diagram over here, and we're going to assume conventional current direction, meaning from the positive terminal to the negative terminal, but it wouldn't make any difference to this discussion anyway. This circuit has a 12-volt cell. That means that the electrons are going to leave the cell with 12 volts of energy per unit charge. So there is a certain push on those electrons based on the energy in the cell. Now, what's very important to understand is that if I had to check the voltage across the conducting wire, I would get a reading of 0 volts. Now, it's not quite 0 volts, but it's a very, very small voltage, like 0.001 volts. So we consider it negligible. That's because the conducting wire is such a good conductor of electricity, and the resistance of it is so low that it takes just about no energy for the electrons to get through the conducting wire. However, when the electrons reach the first resistor, in this case it is a light bulb, and you will see later I'm going to equate resistors to obstacle courses. That is now where the electrons need to start using the 12 volts of energy to get through the resistors. So when the electrons pass that first resistor, they lose 3 volts of energy of their initial 12 volts. So over here, they leave the cell with 12 volts, 12, 12, 12, 12, 12. They enter the resistor with 12 volts of energy, but they come out on the other side with only 9 volts of energy left to get them through the rest of the circuit. At the second resistor, 5 volts of energy are used, and that leaves 4 volts of energy available to be used in the last resistor. The total voltage that's going to be used by all the resistors in a circuit will be equal to the total voltage of the cell, but we're going to come to that a little bit later. Potential difference simply indicates to us that there is a voltage drop as the electrons are moving through the circuit. The definition for potential difference is the same as the definition for voltage. So if you're asked to define potential difference, you would simply say it is the work done per unit charge. Now, what's EMF? EMF, or electromotive force, is the total voltage or the total potential difference across the cell or the battery. So if you go to the shops and you buy a 5-volt cell, if you had to measure the EMF or the voltage of that cell, you would find that it measures 5 volts. Let's define EMF. It is the potential work done per unit charge in a cell in an open circuit. Remember that when we talk about EMF, we are talking about the voltage of a cell when it is not connected to a closed circuit. So it is either a standalone unit or it is connected to an open circuit, but it is not currently doing anything. So it has the potential to do work, but it is not actually doing work at the moment because it is part of an open circuit. The EMF would be the voltage that you would measure in a battery that is not connected to a circuit. And that brings us to the idea of terminal potential difference. And that is the voltage or potential difference across a cell or a battery when the circuit is closed and running. So again, if you buy a 5-volt cell, before you have connected it to a closed circuit, you would measure an EMF of 5 volts. But once it is connected to a closed circuit and electricity is running through the circuit, you'll find that the voltage across the cell is going to be just a little bit less than the 5 volts. So it would be something like 4.98 volts. That is a slightly lower value than the full voltage of the cell. And the reason for that is that some of that energy is used or some work is being done to drive the charge or to drive the little electrons through the cell itself. Now, in the GDE syllabus, in the CAP syllabus, we ignore this effect in our calculations. In the IB syllabus, these values are taken into account in the calculations. If we were asked to define terminal potential difference, we would say that it is the work done per unit charge in a cell in a closed circuit. The instrument used to measure voltage is the voltmeter, and a voltmeter is always connected in parallel with the rest of the circuit components. So what we mean by that is that the voltmeter cannot be connected along the conducting wire, but it needs to be connected above or below the conducting wire. So here the voltmeter is measuring the voltage of the light bulb. We could also place a voltmeter above the cell, which would provide us with the voltage of the cell. And just as a reminder, if we had to place a voltmeter along the conducting wire, we would get a reading of 0 volts. It takes so little energy for the electrons to move through the conducting wire that it is just about negligible. And the electrons use their energy when they move through resistors. And the energy gets replenished at the cell. And that will continue until the battery goes flat, which we will discuss shortly. Consider the circuit diagram below. So here we've got V3, which is above the cell, and we've got V1 and V2, which are each below a resistor. If V3 is 5 volts and I have 2 identical resistors in my circuit, what will be the voltage across each resistor? Remember, these resistors are obstacle courses, and because both of these obstacle courses are identical, the electrons will divide their 5 volts of energy equally among these 2 obstacle courses. So the answer is 2.5 volts across each resistor. If V3 is 10 volts and V1 is 3 volts, what will be the reading on V2? So remember, the total energy available to the circuit is 10 volts, and this obstacle course uses 3 volts of energy. So what's left for this obstacle course? It is 10 minus 3, which is 7 volts. Now, if these resistors don't have an identical voltage across them, that means that the resistors are not identical in their resistance. V1 has 3 volts across it, and V2 has 7 volts across it. So that means that the electrons spend more energy getting through this obstacle course than through this obstacle course, which gives us an indication that this resistor over here has a greater resistance. If V1 is 4 volts and V2 is 3.5 volts, what will be the reading on V3? Well, we know that the total voltage provided by the cell is going to be equal to all the voltages across the resistors within the circuit. So it would be 4 plus 3.5, indicating that this circuit has a 7.5 volt cell. What will be the voltage across a piece of conducting wire? As already mentioned, the voltage is so low that it is negligible. It's not exactly 0 volts, but we refer to it as 0 volts. And that's because it takes almost no energy for the electrons to cross the conducting wire, which is an excellent conductor of electricity. So it offers very, very low resistance, a very easy path for the electrons. This is a very important concept that you need to keep in mind, and often you will be asked multiple choice questions around this. The voltage across a closed switch is 0 volts, and that makes sense because a switch is just a conducting wire that is there to open and close. So when that conducting wire is closed, it allows current to move through the circuit, and we know that the voltage across a conducting wire is so low that it's negligible, that we refer to it as 0 volts. If you consider this circuit, it has a 12 volt cell. The circuit is running because it is a closed circuit, and we can see here that the light bulb is on. If we place a voltmeter below or above the switch, which is closed, it is acting like a normal conducting wire, and we would get a reading of 0 volts. That makes sense. However, if you take a look at this diagram over here, the switch is open. We still have a 12 volt cell, and we still have our light bulb, which is obviously off because current cannot flow through the circuit. Now, if you had to place a voltmeter across an open switch, you would get the same voltage reading as the voltage reading of the cell. This is confusing. It doesn't make that much sense, but again, you need to keep this in mind because it often comes up in multiple choice questions. The reason is that the voltage across an open switch represents the potential difference, that voltage drop between 2 points of the switch, even if no current is flowing through it. So an analogy would be like a water pump that continues to exert a pressure, so that water is exerting a pressure on the valve, even though the valve is closed, so no water is flowing through it. So on the one side of the valve, we have full pressure, and on the other side, because no water is allowed to travel through, we have zero pressure. And that difference in pressure would be the value of the full pressure minus the zero pressure. It's the same idea here. We have one side of the switch that has the full pressure of the 12 volts and the other side of the switch that has zero pressure. So the potential difference between the two is 12 minus 0, which is 12 volts. Let's discuss what it is that makes batteries go flat. Remember that we defined a cell as an electrochemical unit that converts chemical energy into electrical energy. A cell has two electrodes. It has a positive terminal and a negative terminal. The negative terminal also has another name, which is the anode, and the positive terminal is also known as the cathode. And the anode and the cathode are separated by a substance known as an electrolyte, which is a conducting substance. A cell is designed with chemicals in it so that when that cell is connected to a circuit, chemical reactions take place within the cell. Now, in the positive terminal of the cell, chemical reactions take place, and those chemical reactions result in the formation of charged atoms, and electrons get released from those charged atoms. Now, those specific chemical reactions are called redox reactions, which we touch on very, very briefly in grade 10, but we learn about in great detail in grade 11. Those electrons are then forced to leave the negative terminal of the cell because they don't like the negative terminal, which is full of electrons that repel each other. And then they move towards the positive terminal of the cell because they're attracted to the positive charge of the positive terminal. Now, this, of course, applies to the direction of real electron flow, not conventional current. Over time, as the cell provides power to a device, the chemical reactants that the cell was designed with are converted into different substances because in a chemical reaction, reactants form products. As a result, the cell's voltage decreases until it can no longer deliver power to a device because we run out of chemical reactants because all those reactants have turned into products. That is what we refer to as a battery going flat. Rechargeable batteries can be recharged by applying an external current that reverses the chemical reactions that occur while the battery is providing power. So remember that the reactants produced products. Now, running that electric current through the products allows the original reactants to be regenerated, and that restores the cell's charge and it can be used again. Let's take a look at a couple of examples related to voltage. A battery does 18 joules of work to move 3 coulombs of charge through a circuit. What is the voltage of the battery? So the formula is V equals E over Q. Remember, energy and work mean the same thing, so you can also write V equals W over Q. That's 18 divided by 3, so the voltage of the battery is 6 volts. A 12-volt battery supplies a maximum of 120 joules of energy when a charge passes through it. Calculating the amount of charge passing through the battery. Again, we use the same formula, V equals E over Q, which I have rearranged as Q equals E over V. That's 120 joules divided by 12 volts, so the charge passing through the battery is 10 coulombs. That brings us to the end of voltage. In the next lesson, we will discuss resistance.